Okay, so any questions from the previous class? So we started this abstract data type list, right? We did the mathematical modeling and now we are seeing some implementations of it. So there is an implementation of list via an array, right? So we'll just put every element, ith element is ai, we'll just put it in the ith location of the array. If the array is big A, then it's put in big A I minus 1. That's the implementation. So the only interesting point here was that array location immediately gives you a pointer. It's a series of equispaced addresses, and you know how to move from one address to the next by doing a +1. So that was the only important point, that if array is big A, then big A plus 1, big A plus 2 are the equispaced addresses. And this is why your knowledge of C is important, because this is how C also implements an array. So int array becomes int star of that variable. The type is int star. So let's just quickly recall the complexity of these operations. So all the operations are constant time except search, right? Because it's unsorted data, so search will require order n in the worst case. But unfortunately, insert also requires order n in this implementation, because when you try to insert at an arbitrary location I, or equivalently in the modeling we said we are given a pointer P. So if you want to insert in the list at a place P, then in the array implementation you have to shift everything that follows forward to maintain the equispaced addressing. Otherwise, if you put it just in the middle of two pointers, two addresses, then the addressing will not be equispaced. It will become smaller, it will become closer. So to make it equispaced, you have to again shift it forward, or in the delete case backward. Now these two operations are important operations. This is how you build a list. So since insertion deletion are important operations in practice, we need to optimize them. Because otherwise, just to build a list, implement a list of size n, it will take n square time, order n square time. So the second idea which will solve this problem is through linked list, right? So now you will use a link based or pointer based. So this is in particular for C programming. So some languages don't have pointers, and Java has a different way. It is not exactly pointers of C. So when I say pointer, I will mean C language, which I think is the same in C sharp and C++ also. So we'll use pointers, and this is called linked list or link based implementation. of this ADT list. So that is something where we will not care about equispaced addresses. Okay, so addresses will be randomly located in the hard disk. So then if they are randomly located, how do you go from one cell to the next? You have to store the address, right? So instead of doing A plus I, you have to actually use store and use that address. So we can see that in a diagram, which will be useful all the time. All the time you will be using this diagram. So here, let's take so the list is suppose 391. Okay, these are the elements unsorted, 3 elements. So first cell will contain 3, but it will also contain pointers. And similarly, second will contain 9 and pointers, and then 1 and pointers. And then it will end. So now the pointers, which is the important part, these are so there is a pointer to the next and there is a pointer to the previous. Okay, and how do you know where the list starts? So then you have to keep a pointer to the whole list, right? So for that purpose, you should point to the first cell and call this pointer head. Okay, so head is not a cell; it is just a variable storing the address to the first cell. And these crossed cells are basically null pointers. Okay, so or you can call it EOF. So this is end of file pointer and this is end of file pointer or null. So you start with the head variable, it stores an address, then you go to cell containing 3, and then the next pointer will take you to 9, which will then take you to 1, which will then take you to EOF where the list has ended. Okay, so the list is now can be traversed in at least from head to null. It can EOF it can be traversed. What if you wanted to traverse backwards? Yes, so you can keep a tail variable also. We will not be doing that. But if you reach last cell, which is containing 1, then from there you can traverse back because there is a link, there is a chain using these previous pointers. So if you reach the end, you can reach the everything else backwards in the backward direction. So 391 and then you can get 193 in that order. So this is more than what we had promised. So this is called a doubly linked list. Okay, so this, so have you seen any implementation of this in C programming? Because this is usually not done in the C course, but if you have seen it, so then it will help because and if you have not seen it, then you should implement all these things that we'll discuss now, because this can be although very simple in the diagram, it can be quite tricky to implement as a program, because you have to keep checking all these border cases. So you have to do some case study in the C program. So is there any questions about this, what we have done? Okay, so this, so list L is basically just the head. Or maybe we can use list L is accessed so this head variable should remind you of what was the corresponding variable in the array implementation. That was big A, right? So it's like the A variable in array. So there also you had the head variable, but there was additional advantage of once you know A, you know everything. But here if you know head, you don't know all the addresses, because the addresses are really arbitrary. So to get the next address, you have to go to this cell that head points to, and from there you have to read what the next address is. Okay, so there is a big difference, although the starting address is presented as in the array implementation. Okay, so how do you implement insert in this? Suppose I want to insert value x at place P in the list L. Right, so P will point to one of these cells, let us say it points to 9. So at that place now you want to insert x. Right, so when you insert x, what will happen? Do you have to look at 9 and 1 also? Because in the array you had to. In the array you had to look at 9 and 1 and shift it forward. So here when you are already given P, so you only have to look at the cell before P and P, and in the middle you just create a new node and insert. Okay, you don't have to look at what is before 3 and what is after 9. So this is the advantage here. So you can now implement insert completely locally. So say P is pointing to 9. So then you have to work with this 3 P and X, and you can ignore the rest. Okay, this is the advantage of list as a linked list. So let us now look at the implementation of this. So completely locally, you will see 3 pointing to and you will create a new node. So now, so there are these things which we are ignoring. There are these connections forward and backwards which we will not care about. And the change we want to do is that we want to cut this link, these links, right? Because we want. So what is this? This is the P that is given to you, and this is the T that you can find out from P. So you know the pointers P and T, and you have just created a new node X in some address. That address also you know. Let's call it Q. So you have these three addresses or locations T and PQ. How do you now insert this Q in the list? Yeah, so you cut the green line links and make new links, which means that instead the next of 3 should be this, and the previous of X should be this, and symmetrically here. Okay, so these 4 plus 3 pointers, 7 pointers is what you have to work with in your C program, and the original 2 green pointers you have to, I mean they will automatically get killed because the next green link will instead become this red, and same thing with the previous of 9 will automatically become X. So it will be, so that information will be lost. The thing which is crossed will be lost, and now the new list will be bigger by this one cell that you have created. So that's what you have to do in C programming. Okay, so P is given to you, which means that you should find out T. So what is T? Yes, so let's say P is pointing to some struct variable. So the struct variable, the struct variable has 3 values, right? It has next, previous, and the number, the integer, 3 things. So P is pointing to a struct. So P left is what you want, P dot left. That is T. So now we know P and T, we have to create Q. So let us create Q as a new node. So node is basically just a struct. Something in this. So whatever is that declaration, using that you create a new instance of node. Q will point to that, and then you set the data in Q, right? So which means what is Q dot val, that is given as X. What is Q dot left, that you have found to be T, and what is Q dot right, that is P. Okay, so XTP is stored in Q now. So now Q is well prepared. Now we have to focus on changing the links of T and P. So how do you do that? So what is T dot right? Yeah, so first you change T dot right to Q, and P dot, yeah, P dot left you change to what? Q. so at this point I think we have completed. So Q was completed in those three lines. This completes Q. This completes T. Because in T you only need to change the right pointer. You don't need to change the value and the left pointer. So this completes T, and last line completes P. Okay, so all these three cells are completed. You have to check this code, and then you have to check the correctness of the code, which is that it gives you the new red links, a new list. So L is updated. So now its size is n plus 1. So whatever was the original size plus 1. Okay, so this is the long code where every step is a pointer manipulation. Okay, so you should implement this in C and check that it works. And what is the complexity now? So this insert XPL takes how much time? So I mean, assuming that the pointers are constant size, values are constant size, you can check that every step here in the code is constant time, right? So with that understanding, this is constant time. It doesn't have any loops. There is no for loop. There is no full search of the list. Yes. Mm-hmm. Yeah. So for that you have to look at the declaration of the function. The function insert in the abstract modeling of the list needs three things: the value, the pointer, and the list. So here you are already given head, P, and value X. You don't have to start from head and reach P. Yeah. Yes. Yeah, so this is what I said last time also, that we are completely ignoring how the head of the hard disk will move. It may have to move from this to 1 kilometer away. We don't care about those mechanical details. Logically, the thing is that the address is known to the postman here, that the letter has to be delivered to this address. Instead of the array implementation where the address, all the addresses were known, but then there was no way other than going through each and every house. So here you don't have to go to each and every house. You can directly go to that address, which comes, which is basically related to, I mean, there was this problem with array, that array is random access, which seems to be a strong advantage, but it also is a problem, because then when you insert at some arbitrary location, everything after that has to be shifted forward. That we are not doing anymore. We are not shifting. In fact, we are not even looking at any other cell except these three cells. So it is what you are saying will be the complexity of the operating system, not of your program. No, it's not about accessing, it's about what your insert code will do. The code itself will look at each and every cell, which here the orange code is not looking at. this complexity is only of this orange code. It is not of operating system. So the operating system may be doing other things. We cannot guarantee anything about that. Whatever you are talking about is a problem with the operating system. It's not a problem of this code. This code gets address P and it can directly reach P in a nanosecond. Now, if it is not a nanosecond, if it takes more time, then that is a problem with your hardware. I mean, that we cannot. So this solves the first problem, then the hardware problem you have to solve next. We will not do that in this course. So the way that is solved is you have to make sure that all your data is placed in very close vicinity on the hard disk. So it is as close as possible so that the movement from one address to the next doesn't take long. But that is not our job here. I mean, you cannot control the operating system because you have to assume that the operating system is a universal machine which can do whatever you say in this course. It's not easy. It's by definition trivial. If I give you the address that the data is stored at address OX123, then when my program wants to access that access is immediate. No. P is the input here. What do you mean get P? Why not? That is the ADT we are talking about. The abstract data type here is that you have been given an address. We are not solving any other problem. So we are just solving what the job requirement was. So the job requirement here was this update operation insert XPL, you have to insert X at location P in the list. It's already given. This is the job you have to do. Everything else is a bonus. And even this, the array was not able to solve while the doubly linked list solves. Okay, so this takes order one time. And you can do yeah, so I guess if it is still not clear, then you stay with this question, why is this faster than array? Why is the array implement significantly slower than the linked list implement? So the answer is you have to write down both the pseudocode and then compare just the pseudocode. Don't worry about what the OS will actually do. That's not our problem here. Our problem is only to compare the two pseudocodes. You will see that in one pseudocode there is a loop of length n, while in this pseudocode there is no loop. Everything here is transparent, just constantly many. If you count the steps, you have just 6-7 steps, independent of n. That would be your answer. And second is, yeah, you can generalize this or you can just trivially adapt this to deletion. So when you want to delete a location from the list. So do this pseudocode. So what would be the diagram for this? Suppose now you want to delete 9. So there is no new node creation. So this again is T, this is P, there is no Q anymore, and you want to delete this P from the list. So list has to become size from size n, size now it has to become size n minus 1. What do you do? In constant steps? Yes, so there is something which I should have drawn here. This will need now P dot next, right? Which probably was in our example 391, so that was 1. So you have to actually go to the next. So this can be called Q now. And what you want is to get rid of this guy. Right, so you delete, so to forget about 9, all you have to do is update Q dot left. So update Q dot left to T and T dot right to Q. So then all these links will be gone. And when they are gone, then it's as if 9 is gone. Right, so now after 3 you get 1. So again you can ask what will be the cost of losing 9. So those things is again a problem of the OS. So it is up to operating system to reuse those spaces which have been freed to do some other job. Right? So on your computer maybe you have a Internet Explorer open and maybe you have a Chrome open. So if Chrome removes 9, then it is OS's job to give this 9 to Internet Explorer if it wants. Okay, so reallocation of space will be the job of operating system. We don't care about what will happen to old data of the list. We only care about what our pseudocode is for delete. And so with that understanding, this delete is also order 1 time. So the freed space is handled or reused by the operating system. Which we won't care about. Okay, so in practice, these will be the additional problems or the next problems, but that is not the job you are being asked to do here. So you solve the first part, second part will be studied in OS. Because the problem in practice that will happen is you have a list where you have put everything close by on the hard disk, but then when you delete, then there will be fragments. So the deleted part is now uncharted space, which will be given to some other list, L prime. So now L and L prime spaces will be interleaving. They will not. So this will force your list to have memory spaces very far apart. So then your hard disk head has to move very far. Right? So those will be practical problems, but this is not your concern here. You cannot solve everything at once. Okay, so let's do the next one. which is successor. So what is the successor of a location in the list L? How do you do this? Yeah, so this one is easy. It's the same thing which you did in the array implement, not much changes. When you want to find the successor, then you should just take that location, get the struct, and use its right pointer. So there are three variables here in the struct: left, val, and right. So from P you can extract all three, and you can use in here the right one. So Q is P dot right, and return what? Return Q dot val. Okay, so Q dot val will give you this value. This is what is being outputted, the red cell. And similar thing for predecessor, right? Then you should go to P and left. Okay, so yeah, so other things are similar. So this gives you the result that linked list has complexity so is empty, L has complexity. Yeah, that is as trivial as for array search whether X is in L. Yes, so it is O of n like array, but still when you implement it, the code will change slightly. So instead of, so in the array case you were moving with the big A plus I, and here you have to use the right pointer to move forward. Right, so the pseudocode will change, but the logic doesn't change. It's the same amount of time, which is big O of n. So I shorten successor to SUCC. This is as already checked, order 1. Predecessor, PRED. That's also order 1. Create empty. So create empty is order 1. No problem there. Insert and delete we have done. At pointer at location P, that's order 1, and delete. For what? Sorry? Space. What is space? Well, this is time complexity. So time complexity also upper bound space. You cannot use more space than the time you have spent. So this is simultaneously time and space. And yeah, like create empty, make empty is the same. These are trivial. This is also constant time, although here again one should remember that the space reuse is done by OS. So when you have let's say you have billions of entries in the list, and then you in one operation you make it empty, it doesn't mean that you will have to go through those billion entries and make them, free them up one by one, because it will be then order n. So here make empty pseudocode will just change the head. It will just say that now the head is pointing to null cell. What happens to all that space which you were occupying before, that is the job of the OS. Right? So don't confuse the operating system's order n time with this, because you are not writing operating system code here. Sorry? No. So OS gives permissions to a process like your pseudocode to run. When your pseudocode or when your algorithm says, or when your process says that I'm not accessing this space, then now you have given your permission back to the OS. So OS can do with that space whatever OS wants. So usually some 100 applications are running at the same second in your computer. So one of these 100 applications will get that space. But that is not your pseudocode, it's OS's pseudocode. Your pseudocode is already analyzed here in blue complexity. Okay, don't confuse this with everything which happens in a computer. You are not yet at that stage. So when you code for OS, then at that time you will worry about that complexity. And yes, the same thing with delete. Okay, so I think that's all here. So this, by the way, is called, I guess one word is garbage collection. So your pseudocode is not responsible for garbage collection, it just creates garbage, but now the OS has to do this garbage collection part, which confuses you. Sometimes you think that it should be order n, but that's not your job. Okay, you can have n entries in the list, you can simultaneously make them empty in constant time. Okay. Yes, so as a good exercise, implement these in C. So write a program to implement these. So the language we are using in discussions is just C. So in C, the pseudocode will be very similar to what we have written here. I mean, of course, you have, so the reason why it's not just a copy paste job, you cannot directly copy paste this into C program, because, so for example, when this, so P is a pointer, right? Pointer to a struct. So how, you cannot really write P dot left. So you have to write maybe star P and after that left, right? So there will be some changes in the way this is written. So it's a good exercise to actually implement this. So here we are being a bit casual with the operators. So dot and arrow is not exactly as C will do it. So this is only a pseudocode, it's not guaranteed to be a C program. So the details you can check in actual implementation. Okay, so yeah, so this is still an ADT that we have developed, right? Let's see an example where you will use this. So example for the list ADT. So we have developed, we have modeled this ADT, and we have also implemented it using array and list. So example is maintain a directory of names and their telephone numbers as a list. As a list L with the operations. So obviously for a list, for a directory, the operations you would want are, you want to search for a name, so in the list, say linked list, you have to search name X, and wherever you find it, you have to then output the corresponding telephone number or address. And as people get phone or they change their phone, you have to insert delete. So insert a new record. Deletion will be similar. So record is name and let's say phone number. Okay, so let's compare the two implementations that we have. So first one was using array, and the second one was using list link. So in the array implementation, how much time? So assuming that the list, the directory has n names or n records, what is the complexity of searching a name? No, right now in the list ADT there is no guarantee of sorting. Yeah, so since it's unsorted, so this will be, both will be order n. And for insertion, yeah, this is the same thing. We are just repeating. So this is order n, this is order 1. So what we would want is, we would want to get the search also very fast, right? So we would want to maintain a sorted list. Uh, yeah, you are. Yeah, it's a good question. So inserting a new record, it can also be order 1. Depends. If you just insert in the end, it can be order 1. So what we want is, we want both these operations, search and insert, both of them to be order 1. That's the question we can leave with. So question is, no. So what he meant is that if we are not sorting, we can actually put it at the beginning of the array or at the end of the array. Uh, Yeah, that is a genuine, yeah, so this may not be possible, depends on the implementation. Right. So which is going towards actually linked list. So I think technically we can say that array will require order n. So what we want is we want both of these things. Uh, I mean, if this was sorted, then we could have searched in order log n. So can we get both these properties? So can we get the best of both worlds? Okay, so next time we will try to get the best of both these. So if the array is maintained sorted and it is, you do binary search, the complexity is only order log n because of again random access, while in the linked list adding is constant time. So can you make both of them constant time or maximum log n in the same implementation? Okay, thanks.